A system of two linear equations in two variables is a set of two equations, each containing up to two variables. For example, the set of the equations x plus y equals 5 and 2x minus y equals 10 is a system of equations. Individually, each of these equations has an infinite number of solutions. For example, 0, 5 is a solution to the top equation because if I substitute a 0 for x and a 5 for y, that would result in a true statement. 0 plus 5 is in fact 5. Another example of a solution would be 2, 3. If I substitute a 2 for x and a 3 for y, 2 plus 3 would be 5. 4, 1 is another solution. 5, 0, an x for 5 and a 0 for y would be a fourth solution. And like I said, there's an infinite number of solutions to x plus y equals 5. If I plotted these solutions on a coordinate plane, they would line up in a straight line, and that line is called the graph of the equation. 2x minus y equals 10 also has an infinite number of solutions. For example, if you let x equal 0 and y equal negative 10, then 2 times 0 minus negative 10 does equal 10. 0 minus negative 10 or 0 plus 10 is 10. Another solution would be x equals 3 and y equals negative 4. 2 times 3 is 6 minus negative 4. 6 minus negative 4, 6 plus 4 is 10. 3 negative 4 is a solution to this equation. So is 4 negative 2. And so is x equals 5 and y equals 0. If I put a 5 in for x, 2 times 5 is 10, minus 0 for y does equal 10. There is only, although individually each equation has an infinite number of solutions, there is only one ordered pair that is in the set of solutions to both equations. And this is called the solution to the system. A solution to a system of equations is an ordered pair, x comma y, that is a solution to both equations. In this case, the only solution to this system of equations is x equals 5, y equals 0, written as an ordered pair, 5, 0. In this video, we'll discuss three methods to solve systems of linear equations in two variables. So now I will discuss three ways that systems of equations with two equations and two variables can be solved. After we take a look at all three methods, you can decide which one you would like best. You could use that for solving most systems of equations. However, some systems of equations lend themselves to be solved easier with one method or another, and you'll get better at choosing which method is best with a little practice. The three methods that we'll discuss today for solving systems of equations are the elimination method, the substitution method, and graphing. The first method we'll discuss for solving systems of equations is the elimination method. Systems of equations can be solved using this method in 4 steps. The first step is to rewrite the equation so that the constant for both equations is on the right side. You want to move the terms with variables to the left and the term with a constant to the right. For example, the equation 3x plus 2y equals 7 has the constant on the right. Then, the step that's a little more difficult is that you want to rewrite the system so that the coefficients on one of the variables, it doesn't matter which one, the coefficient on one of the variables are opposite numbers. For example, if the coefficient on one of the variables is 2, you would want the coefficient on the other variable to be negative 2. Or if the coefficient on one was 7, you would want the other to be negative 7. For example, if in the system of equation that includes 3x plus 2y equals 7, the other equation was 5x minus 4y equals 10, this system does not yet have two variables which have opposite coefficients. The coefficients on x are 3 and 5. The coefficients on y are 2 and negative 4. Those coefficients have opposite signs, but the numbers themselves are not opposite. What we can do to make the coefficients on the y opposite numbers would be to multiply both sides of the top equation by 2. That's not changing the value of the equation in any way, since you're multiplying both sides of the equation by that number, but what it does do is allow you to rewrite it in a form in which the coefficient on y is positive 4. And that fulfills step 1 because the bottom equation, 5x minus 4y equals 10, now has an opposite coefficient on the y's. We will discuss this process in detail when we do our example for solving a system by the elimination method. After you have two equations with a constant on the right and a pair of variables with opposite coefficients, you'll move on to step 2, which is to combine the equations by adding the like terms on both sides. You'll combine the like terms on the x and the y, and you'll combine the constants. This will eliminate one of the variables because the coefficients on one of the variables are opposite. When you combine like terms, one of those variables will have a coefficient of 0. It will be eliminated from the equation. Solve for the remaining variable. And after you solve for the remaining variable, you'll be able to substitute that result from step 3 into either original equation, and that will give you the value of the other variable. These steps will make a lot more sense when we follow the steps in an example that we do right now. Let's follow those 4 steps and solve this system of equations with the elimination method. Step 1 says to rewrite each equation so that the constant is on the right. And in this system, that is already the case. In both of these equations, the constant is on the right side. Next, we want to rewrite it so that the coefficient on one of the variables are opposite. Now, the coefficients on x are 8 and negative 16, not quite opposite. The coefficients on y are negative 6 and 7. If I take a look at the smaller coefficient on y and think about what I could multiply that by to get up to 7, there is not any integer that I could multiply 6 by to get 7. However, there is an integer that I could multiply 8 by to get up to 16. That would be simply 2. So I can multiply both sides of this equation, both sides of the top equation, by 2 to make the coefficient on the x's opposite. And that's what I'll do. If I multiply the 8x by 2, I'll get 16x. Negative 6y by 2 is negative 12y. And negative 20 times 2 is negative 40. I'll leave the bottom equation unchanged. Negative 16x plus 7y equals 30. And I now have two equations where, I'm done with step 1 because these two equations each have the constant on the right, and one of the variables, the x in this case, has opposite coefficients. One is 16 and the other is negative 16. On to step 2, which says we're going to put the equations together. We're going to combine like terms on both sides of the equation. 16 and negative 16x adds up to 0. That's eliminated in this step. Negative 12y plus 7y is negative 5y, and negative 40 plus 30 is negative 10. Step 3, solve for the remaining variable. If you do step 1 and step 2 correctly, one of the variables will always be eliminated, and then step 3 is to solve for the remaining variable, which in this case can be done in one step. I'll simply divide both sides of the equation by negative 5, and y equals negative 5 divided by negative 10 divided by negative 5 rather, which is positive 2. So I have not yet solved this system, but I do know the y value of the solution is 2. When solving a system of equations, it's often best to write your answer as an ordered pair, an x and a y ordered pair, and the y-coordinate of that ordered pair, the y-coordinate of the solution, is 2, positive 2. Step 4 says take that value and substitute it for y into either one of the original equations. I guess I'll substitute this y into the original top equation because those numbers are a little smaller, but it really doesn't matter. But instead of writing 8x minus 6y equals negative 20, substituting a value of 2 for y gives me 8x minus 6 times 2 equals negative 20. Solving this equation is fairly straightforward. 6 times 2 is 12. I'll add 20 to both sides of the equation, or add 12 to both sides of the equation. Negative 20 plus 12 is negative 8. And then dividing both sides of the equation by positive 8 yields negative 1. The x-coordinate of the solution to this system is negative 1, which means my final answer, written as an ordered pair, is negative 1, 2. The solution to this system of equations is negative 1, 2. Now, I'm not going to write out a check in this example, but you could check this by substituting a negative 1 for x and a positive 2 for y into either one of the original equations. In the top equation, that substitution should result in negative 20. In the bottom equation, that result should evaluate to be positive 30. You can check your answer by substituting the x and y coordinate in for x and y into both original equations. You know you are correct if it makes a true statement in both of the original equations, which in this case it would. The solution to the system is negative 1, 2. Next, we'll discuss solving systems of equations by the substitution method. Like the elimination method, there are 4 steps in the substitution method. The first step is to solve one of the equations for one of the variables. And to make it easier on yourself, if it's possible to avoid fractions in this step, you should do it. We'll discuss this a bit more when we do an example. So you want to take the 2 equations, look at the 2 variables in the top equation, the 2 variables in the bottom equation, and isolate one of those variables. It doesn't matter whether you choose which equation you choose, but you're going to get one of the variables by itself. Then you'll substitute that resulting expression into the other equation. It's important you use the other equation, not the one you used in step 1, but the other equation. After you do that substitution, you'll have an equation with one variable, and you'll solve for that variable. After completing step 3, you'll have one of the values in the ordered pair, either the x or the y, that is the solution to the system. Once you have that one value, just like you did in the elimination method, step 4 is to substitute that value into either original equation, and you'll be able to solve for the other value in the ordered pair that represents the solution to the system. Next, we'll complete an example using this substitution method, and hopefully these 4 steps will become clearer. Let's do that now. Our example will be to solve the system, which includes the equations 7x plus 2y equals negative 19 and negative x plus 2y equals 21. The first step when solving a system by substitution is to solve one of the equations for one of the variables. You actually have 4 choices in this step. You could solve the top equation for x. You could solve the top equation for y. Your third choice would be to solve the bottom equation for x. Or you could solve the bottom equation for y. And really, it doesn't matter which of those you choose. All 4 of those options will give you the correct answer. However, when listing the steps, I did say that it might be easiest if you avoid fractions in this step if you can. If I were to solve the top equation for x, I would have to divide both sides of the equation by 7 at some point, which would involve 2 divided by 7 and 19 divided by 7, which would be fractions that could not be reduced. Likewise, if I solved the top equation for y, I would have to divide everything on both sides by 2, again resulting in fractions. If I took the y in the bottom equation and solved the bottom equation for y, I would have to divide everything by 2 as my last step, and I would end up with 21 divided by 2, which also would be fractional. Now that's not too big of a deal. You could work with that and still arrive at the final answer, but it would be easiest to complete this problem if I solved the bottom equation for x. Because the x doesn't have a coefficient, I will not have to do a division at the end of my solving for x. So what I'll do is I'll take the bottom equation and I'll solve it for x. To solve the bottom equation for x, I'll first subtract 2y from both sides of the equation. Subtract 2y from both sides, and then I haven't quite solved this for x yet because there is a negative in front of the x. So what I'll do is divide every term on both sides of the equation by -1, which yields x equals -21 plus 2y. And this is the result of step 1, solving one of the equations for one of the variables. I chose to solve the bottom equation for x. Next, I'm going to take this expression, -21 plus 2y, and I'm going to substitute it for x in the other equation. So I started working with the bottom equation, solved for x. Now I'm going to take this expression that I found x to be equal to, and I'm going to substitute that for x in the other equation. I'm going to take this top equation, and I'm going to replace the x with what I found x equal to be, -21 plus 2y. So instead of writing 7x here, I'm going to write 7 times -21 plus 2y. And then I'm going to copy the rest of the equation as it was in the original problem, plus 2y equals -19. Now I have a little bit of algebra to do for step 3, which is to solve for the variable. After completing step 2, there's only one variable, y. So I can solve this simple linear equation and get a value for y. And the hardest part of this might be the multiplication. 7 times -21 is -147. 7 times 2y is 14y. Plus 2y equals -19. Now in the next step, I'm going to combine the like terms. 14y plus 2y is 16y. Then I'll add 147 to both sides of the equation. I'm working to isolate the y. And after you add 147 to both sides, you have -19 plus 147, which is 128. And although this is not the case for every system of equations, this division divides evenly. 128 divided by 16 is exactly 8. You could get a fraction decimal here. It doesn't mean that you did anything wrong, but in this problem, the solution for the y is an integer. Y equals 8. Again, I'll write this as an ordered pair. The y value of the ordered pair is 8. One more step. I'm going to take this value of 8 for y, and I'll substitute it into either one of the original equations. Doesn't matter which one on step 4. I'll choose the bottom equation, -x plus 2y equals 21, because those coefficients are a bit smaller than the coefficients in the top equation. So instead of -x plus 2y equals 21, I'll write -x plus 2 times the value of y, 8 equals 21. Simplifying, the product of 2 and 8 is 16. -x plus 16 equals -21, or equals +21 rather. I should not have a negative sign there. I'll then subtract 16 from both sides. -x equals 21 minus 16, which is 5. Now this is not the value of x. This is -x equals 5. So I'll divide both sides by -1 and find that the value of x in the solution to this system is -5. Writing my final answer as an ordered pair. The x-coordinate of the ordered pair is -5. The y-coordinate is 8. The solution to this system of equations, using the substitution method, is -5, 8. The last method we'll talk about for solving systems of equations is the graphing method. The graphing method only has 2 steps, but the first step involves some graphing. However, if you're able to easily and accurately graph each equation in the system, the solution to the system is fairly easy. The first step to solve a system of equations by graphing is to, well, graph both equations. And you want to graph them on the same coordinate plane. If you're doing this by hand, you want to write neatly, take your time, because accurate graphs are required. Once you have the graphs, though, the work is done because the solution is simply the intersection point of the two graphs. The ordered pair, the x and the y value where they intersect, is the solution to the system of equations. Let's now solve a system of equations using this graphing method. The system of equations that we'll solve by graphing is y equals negative 3x plus 4 and y equals 3x minus 2. The two equations in this system are already in slope-intercept form. If you were attempting to solve a system of equations by graphing and the equations were not in slope-intercept form, that would be a good first step. But in this case, the equations are already in a form that makes them easy to graph. The top equation, y equals negative 3x plus 4, has a slope, the coefficient of x, is negative 3 and a y-intercept of 4. Let's begin graphing this by plotting the y-intercept of 4. And because the slope is negative 3, I can find another point on the graph, since the slope is negative 3 or negative 3 over 1. I'm going to go down 3 units and to the right 1 unit to find the next point, another point on this graph. To make sure my graph is as accurate as possible, since I'm drawing this by hand, I'll again go down 3 units and to the right 1, down 3 more units and to the right 1 unit. And now I have 4 points that all would be on the graph of this equation. These 4 points all represent an x and a y. That would be solutions to the equation y equals negative 3x plus 4. As carefully as possible, join those points with a straight line. That straight line is the graph of y equals negative 3x plus 4. Now let's take a look at the other equation in the system, y equals 3x minus 2. This equation has a slope of 3. Rise over run would be 3 over 1. And the y-intercept is negative 2. The value of b, the constant, is negative 2. We'll begin by plotting that y-intercept of negative 2. And then to get to other points on this graph, we'll use the slope, rise over run, 3, up, 1 to the right. Up 3 units, 1 to the right. Up 3 units, 1 to the right. Could also go in the other direction. Instead of rising 3 units and moving to the right 1 unit, you could fall 3 units and move to the left 1 unit. These 4 points are all on the graph of y equals 3x minus 2. They all represent an ordered pair x and y. That would be a solution to that equation. And if we join those 4 points with a straight line, we have the graph of y equals 3x minus 2. Now, the solution to this system of equations is simply the intersection point. And so if I carefully look at the two graphs, I can see that their intersection occurs at the point 1, 1. The solution to this system is the point when x equals 1 and y equals 1. Again, the best way to write the solution to a system of equations is as an ordered pair, 1, 1. This solution could be verified by solving the system by the elimination method or solving the system by the substitution method. Regardless of the method used, you would find the solution to be 1, 1. Additionally, this solution could be verified with a graphing utility. If you have access to a graphing utility and graph y equals negative 3x plus 4 and y equals 3x minus 2, you would see that the intersection point is in fact 1, 1. So, we've now discussed 3 ways to solve systems of equations.